Yeah, good morning, every one of you. So, until the last class, we have seen many mass transfer coefficient and diffusion. What is the phenomena which is happening inside this diffusion chapter? So, today we are going to see the mechanism, how the mass transfer will take place. We are telling that from CA1 to CA2, the concentration will be reduced. From pressure PA1 to PA2, the pressure will be reduced. By that, mass transfer is taking place from higher concentration or higher pressure region to lower concentration or lower pressure region. But how the inside mechanism is happening? Okay, we will see that mechanism. So that mechanism will be described by the three most popular theories, which are called film theory, then penetration theory, and surface renewal theory. So that theories we will see along with the two film theory also. Yeah. So these theories are there, theories of mass transfer. So how the mass transfer is taking place from one phase to another phase, how the concentrations are changing, that is given by film theory. Then next penetration theory is there, surface renewal theory is there. These two theories are the unsteady state theories, and this film theory is the steady state theory. Then based on this film theory, there is a two resistance theory or two film theory we will call, that we will deduce one final equation. Okay, big derivation will be there regarding that. So film theory. Okay, the film theory was proposed by the Whitman. He is the author. He has proposed this Whitman theory. So according to this film theory, whenever there is a mass transfer taking place, convective mass transfer is taking place. So what happens? There will be some film will be formed. Okay, some thin film will be formed with a thickness of that film as Z or delta. Okay, film thickness as delta. So through this film only the mass transfer will take place. Okay, whenever you, for example, if you assume there is a gas phase and liquid phase, a thin film from the gas phase, this solute is transforming to the liquid phase. Then a liquid film will be instantaneously will form. Okay, this thin film will be formed. From there, the concentration will vary within this film only. After this film, there will be the uniform concentration or this stagnant concentration or a bulk concentration CAB. So that how to with respect to the this film, that is given by Whitman's film theory. So I will explain you clearly. So first theory is a film theory. Theories of mass transfer. Okay, then first is film theory or Whitman's film theory we can call. Okay, whenever okay, for example, there is some tower is there. Okay, whatever the tower it may be, tower is there. Gas is entering from the bottom and liquid is entering from the top. So liquid will be flowing like this and gas will be flowing from the bottom to top. And at one junction, they will be interacted with each other. That is called interface. Interface also we can call, or interface also we can call. Okay, this is gas liquid interface. Okay, what this film is saying is to occur a mass transfer, a thin film of liquid will be formed like this, whose thickness will be delta. He is telling that the instantaneous film will be formed whose film thickness is delta. Then a component A, for example, the component A is there, that component concentration will be reduced like this within the film. Okay, within the film, this is Ca naught concentration initially present or at 0. Okay, at film thickness is equal to 0 and at the film thickness equal to delta. Then the overall mass transfer zone is Z. This is axis, x axis. Then this is concentration. Okay, concentration on the y axis. Whenever mass transfer is taking place, a instantaneous film with a thickness delta will be formed. Throughout this film, the concentration of component A will be changing like this. And after this film, the concentration will be uniform. Okay, like this stagnant concentration. This is bulk concentration, CAP. So this is constant concentration. It is not varying in this region, but this region is stagnant. Okay, there is no variation in concentration in this region, but in this in this region there is concentration varies. Concentration varies in this region, but here the concentration will not vary. The film theory is telling that whenever mass transfer is taking place, instantaneous film will be formed. This film will be allowing the component A to transfer into some other fluid. Okay, to transfer into some other fluid which is within this liquid. So the concentration will be varied from one concentration level, that is initial concentration Ca0 to final concentration something, some interfacial concentration something. Then from this interfacial concentration, this concentration will be same as the bulk concentration. So that is said by film theory. So what are the assumptions which are offered by this film theory? Okay, there are assumptions are there for this film theory. Okay, then first assumption is mass transfer occurs by, I am writing in a short form, mass transfer MT. Okay, mass transfer occurs by molecular diffusion. Okay, whatever now we are studying now, that is entirely the molecular diffusion. Mass transfer occurs by molecular diffusion through a fluid layer. Through a fluid layer, or this fluid layer can be called as a film. Through a film at phase boundary. At phase boundary, or we can call this is solid wall. Okay, again it's the solid wall. Okay, one film layer. Okay, one fluid layer will be formed, that is called film. Okay, mass transfer will occur throughout this film. That is the first assumption of this film theory. And second one will be this one. Okay, the continuation for this one. At phase boundary only, this concentration variation will occur. After this film thickness, there is no variation. Then beyond this film, okay, that fluid layer, concentration is homogeneous, or we can say that is bulk concentration CAB. Okay, Ca0 is the initial concentration. Then this is bulk concentration. Okay, delta is a film thickness. Okay, delta is a film thickness. So the second assumption will be the mass transfer through the film occurs at steady state. Okay, MT in the film occurs at steady state. Can anybody tell what is steady state? What is steady state? Okay, change in any quantity with respect to time is 0. Okay, it is independent of time variable. That is called steady state. Then next one is flux is very low. For example, if you assume the flux is very low and mass transfer occurs at low concentration. Okay, the film will be usually very thin. So because of this, the net flux will be 0. So we know that relationship between fluxes. So can anybody tell what is the relationship between fluxes? Relationship between fluxes. That is
NA equal to
NXA plus JA. When net flux is 0, the flux is very low, N is equal to 0. Then this will be 0. Therefore, NA is equal to JA. Okay, this relationship is valid for 4 cases we have seen now. This relationship is valid for A through non-diffusing B or equimolar. Is it equimolar or A through non-diffusing B? Can anybody tell?
A through non-diffusion B.
No, wrong. This is equimolar. A through non-diffusing B will be Na is equal to some constant, Nb is equal to 0. This is A through non-diffusing B, where N is equal to 0 or Na is equal to minus Nb. This is equimolar counter diffusion. So this is N is equal to 0. Na is equal to N, Ja is equimolar counter diffusion. So this is the case of equimolar counter diffusion. We know from the Fick's law, Fick's first law. What is Fick's first law? Ja is equal to minus
Dou CA.
DAB dou Ca by dou Z. Okay, from this equation we can substitute in place of Ja that one. That is Na is equal to minus DAB dou Ca by dou Z. Then we can interchange these variables, that is dou Z is equal to minus DAB dou Ca. Then we have to integrate this within the limits. So what is the limits here? For example, when the concentration is initial concentration, your thickness of the film or your mass transfer zone will start at 0. When Z is equal to 0, yeah, when Z is equal to 0, your concentration is Ca naught. When Z is equal to some film thickness delta, delta, then your concentration is reducing to bulk concentration. Throughout this bulk concentration CAB, that is when Z is equal to some delta, your concentration is a bulk concentration. Now we can integrate this one, that is derivative integral, and this derivative, this integral will be cancelled. This is direct simple integral, that is DAB delta minus 0 upper limit minus lower limit is equal to minus DAB upper limit minus lower limit is CAB minus CA naught. Then therefore Na is equal to delta minus 0 is 0. Then this is DAB by delta. Then the left out is this minus is there. To compensate this minus, we can interchange this variable. That is Ca naught minus Ca. Okay, Ca naught minus Cab. Okay, Ca naught minus Cab. Okay, this relationship is valid for laminar flow. Laminar flow. Now we know that what is mass transfer coefficient? The mass transfer coefficient is nothing but flux is directly proportional to concentration gradient or concentration difference. Then this proportionality constant is nothing but mass transfer coefficient. So flux is denoted by Na, mass transfer coefficient. Okay, let us see the concentration gradient. So higher concentration to lower concentration, Ca naught minus Cab. Then mass transfer coefficient will be some K. Okay, some K. This is a liquid film is there. So this is KL. So therefore we can write this DAB by delta is nothing but KL. So this equation will be turned to Na is equal to KL into Ca naught minus Cab. So mass transfer coefficient, flux is directly proportional to concentration gradient or driving force, we can say, in which the proportionality constant is the mass transfer coefficient. We have seen in the initial mass transfer coefficient definition, whatever the flux is there and the concentration gradient is there, whatever the variables left after defining flux and concentration gradients or pressure gradient or driving force, all the terms will be clubbed up together and they will be called as a mass transfer coefficient, where your KL is a mass transfer coefficient, mass transfer coefficient. So for KL is where KL is equal to DAB by delta. So from this equation, what we can say, mass transfer coefficient is directly proportional to DAB, or mass transfer coefficient is nothing but KL. KL is directly proportional to diffusivity, which is valid for laminar flow. Then one another relationship will be there, that is KL is directly proportional to DAB power some N. This is valid for turbulent flow. So what is this N? Okay, this N is nothing but some variable, some constant. Okay, that N will be in the range of 0.0 to 0.9 range. Depending on the operating conditions, this N can be 0 to 0.9. Okay, these two relationship are valid for your turbulent flow and laminar flow. Mass transfer coefficient is defined in this way. Okay, we already know what is this one. This is film thickness. Is that okay? Have you understood this one?
Yes, sir.
Yeah. So there are, yes. Okay. Then there are drawbacks are there, this film theory. That's why there are two other theories will also be coming up. That is film penetration theory and surface renewal theory. The drawbacks in this film theory is, okay, it cannot explain, okay, uh, it is explaining how the mass transfer is taking place within the film. The mass transfer is taking place, it is explaining that one, but how to estimate this film thickness delta, they have not shown us a way how to estimate this film thickness. That's the drawback of this film theory. So, although the film theory offers some explanation of the mechanism, how the mass transfer will take place in the fluid medium, but it does not explain how to estimate the thickness of the film. And this theory is only applicable for steady state. Okay, one drawback is, so it doesn't give the way to estimate film thickness. Way to estimate film thickness. So film thickness is delta. Way to estimate film thickness, which is delta. Okay, which is delta. It does not give the way to estimate that film thickness delta, but it is explained that mechanism is taking place within that film. Okay, that's a fine thing. And drawback is it does not give any way to estimate your film thickness. And next drawback is it is applicable only for the steady state. So whose variables does not change with time. Okay, change in some y by change in time is equal to 0. This is applicable for this situation only. But apart from that this situation, for nothing it is applicable. So if you see the industrial operation, all operations are dynamic. They are carried out at unsteady state conditions. Okay, they are not independent of time. That's why this film theory is considered as a somewhat drawback. These two are the very drawbacks of this film theory. Due to these two disadvantages, these models are restricted to only the mass transfer in the diffusion cells only. Okay, not for the big industrial plants. This theory is not applicable. Okay, then next theories are there, which is penetration theory we can call. Penetration theory. So what is this penetration theory? Now see the film theory. I have given you the explanation. What is this film theory? What is that graph? And these drawbacks are there and assumptions. The final equation I have given here. Okay, you can go through this slide. Okay, if you want explanation furthermore, or if you are there in confusion, you can ask me if you have any doubts. Okay, then we will move to the penetration theory, next theory, which is proposed by Higby. So this is called as a Higby's penetration theory. So this theory, how this theory comes here? Why? Because there is a drawbacks of this film theory. That's why a next theory has been proposed. For example, in the 10th class, you might have seen the Bohr's atomic theory, and many theories will be there. Okay, for the physics. Okay, similarly, one theory is having some drawbacks. That's why yes, next theory has been coming up. Similarly, here also, this film theory is giving some drawback. It is having some drawbacks. Because of this drawbacks only, the next theories are coming. So this theory is called as a Higby penetration theory. So why this theory has been come up? Why? Because all the operations, industrial operations, are nothing but which are carried out at unsteady state conditions, whose variables are not at all independent of time. They are dependent on time. So this penetration theory is valid for unsteady state mass transfer operations. So unsteady state mass transfer operations only, this penetration theory is valid. So how this is valid, I will explain you that one. So for example, there is a same tower. Once again, you consider, okay, liquid is flowing from top to bottom and gas is entering and flowing from bottom to top. and they will be meeting at some certain juncture like this. They will be meeting like this. So this is some interface. So some interface will be there here. So how this is occurring means in all these situations, the variables or concentration, whatever it is there, they are not independent of time. Okay, they are not independent of time. Absorption operation. This is nothing but an absorption operation. In this, the major role is the solute which is present in gas phase needs to be dissolved or transformed or solubilized into this liquid phase. That is the major role of absorption process. So in the absorption of gases from the bubbles, okay, whenever these gases are rising from top to bottom to top, and this liquid is flowing like this, okay, liquid is flowing like this. Whenever the gas is rising from bottom to top like this, whenever they are coming in contact with this liquid, they will be attacking this liquid as a bubbles. Okay, small bubbles will be formed. Okay, bubbling like this. Okay, if you just put a straw into your glass full of water, when you bubble some when you blow some air inside that one, what it will happen? So some bubbles will be produced. So similarly the same bubbles will be happened. If you consider this single bubble, okay, one single bubble, if you project this bubble, if you project this bubble like this, so liquid will be coming from the top to bottom like this. So this liquid will be occupying this gas bubble. So this bubble will be rising from the bottom to top. So gas will be rising from the bottom to top and liquid will be from the top to bottom. So whenever if you take only single bubble, the liquid will be touching this bubble as a small packets. Okay, small droplets or small packets. In the mass transfer operations, we will call these droplets as a packets. So this will be whatever this occupied, no, this is called as a liquid packets. Okay, this is a liquid packets, we can say. Liquid packets. Okay, this is bubble. Okay, outside the bubble, so this is a rising bubble. Why it is rising? Why? Because gas is flowing from bottom to top. That's why this is called as a rising bubble. Okay, from bottom to top it is going, but liquid is falling from top to bottom. Okay, that's why they will occupy the bubble surface like a small packets. Okay, for example, this is packet 1, this is packet 2, or droplet 1, droplet 2, 3, 4, 5, 6, 7. Okay, whenever they are occupying this as a packets throughout this bubble, whenever this bubble is flowing from bottom to top, so once the mass transfer has been completed, so these packets will be falling down. Okay, these packets will be falling down like this. So mass transfer will occur from bubble phase to the liquid phase. Okay, throughout this bubble it will occur. So there are certain assumptions to quantify or to propose this theory. That assumptions are, okay, this is, we already know this is unsteady state theory. This is valid for unsteady state mass transfer through liquid elements, we can say, through liquid elements or packets. Or packets. This is called elements or packets, so long as it is in contact with, it is in contact with the bubble or other phase, we can say. So the mass transfer will be occurring at unsteady state condition so long as this liquid packets are attached to the surface of the bubble. Okay, surface of the bubble or surface of the other phase. Then next assumption is equilibrium exists. So what is equilibrium? Can anybody say what is equilibrium? Equilibrium exists as gas liquid interface. Okay, please try to tell something. Equilibrium. What is equilibrium? You might have seen in the CPP course or this fluid mechanics also. You might have seen equilibrium. Okay, then third assumption is each of liquid element. Okay, that packets or packets stay in contact with the gas for same period of time. Same period. Okay, same period. Okay, okay, for the same time they are staying to each other. So for example, let us see the same assumptions once again. So long as this liquid packets are in touch with this gas bubble, so mass transfer will take place. This mass transfer will take place at unsteady state condition. That is first assumption. Then next assumption is equilibrium exists between these two phases. What is equilibrium? For example, the gas is rising from bottom to top. Okay, the solute will contain, okay, this gas will contain certain solute, and liquid will be coming from top to bottom. Okay, liquid I am denoting like this. Okay, liquid initially, for example, there is no solute. Okay, no solute is there inside this liquid. So what happens? Because the concentration of solute in the gas phase is very high, then concentration of solute is very low, so mass transfer will occurs from higher concentration to lower concentration. So that is from gas phase to liquid phase, the mass transfer will occurs. Okay, as soon as the concentration inside the concentration of the solute inside this liquid is somewhat attained, already some of the solute from the gas phase is transferred inside, then it reaches a saturation, means it has completely been exhausted, that liquid has been completely been exhausted, and that is not having any capacity, further capacity to absorb the solute from the gas phase, then that is called as a equilibrium. Okay, it has been attained a saturation point. Okay, if continuously, for example, let us say if continuously 6 classes has been taken without any interruption for you, what you will do? You will be frustrated, you will be saturated. Okay, you will tell the lecturer that no sir, we cannot take any more. Okay, you should stop your lectures like this. Why? Means you are completely exhausted by listening to the series of lectures. Okay, consecutive lectures, by listening to that one you have been completely exhausted. Similarly here also it will take solute to certain extent. After that extent has been crossed, so it will not have any limit to absorb the solute from the gas phase. So under such conditions we will call this liquid and gas will be in equilibrium. Okay, equilibrium exists between liquid and gas phase, second assumption. And the third assumption is each liquid packet or element will stay for same period of time. Okay, then what about this third assumption means? For example, this is a bubble. Okay, onto the bubble there will be some packets like this. Okay, this is 1, 2, 3, 4, 5. So how these packets are coming? From the top liquid, bulk of the liquid, the packets are coming. After coming here, it will be dropping. Okay, after attaching to the surface, after completing the mass transfer, it is dropping to the bottom. Dropping to the bottom. So next step, what happens? So this 1, 2, 3, 4, 5. Okay, for example, this operation has been taken place for 1 minute. After 1 minute, this 1, 2, 3, 4, 5. Okay, these packets will be dropped. Okay, that packets are 1, 2, 3, 4, 5 will be dropped like this, and a fresh packets of liquid will be coming and attaching to this surface. So that is 5, 6, 7, 8, 9, 10. Okay, after it has been dropped, this packets, liquid packets has been, or liquid elements has been dropped once to the bottom. So a fresh packets will be once again occupying this bubble. Okay, this will happening for a same period of time. Okay, if these packets are dropping, then it will replace, and same this packets. Okay, for 1 minute also, for within 1 minute, this all the packets 1, 2, 3, 4, 5 will be dropped to the bottom, and remaining 6, 7, 8, 9, 10 will be occupying that bubble. Okay, these three are the assumptions. Is that clear? This theory?
Yes, sir.
Yeah. Then next one is this theory will give you one empirical equation, not empirical equation exactly. You have to remember that equation. Why? Because its derivation is very big, but it is not required to derive that derivation. So if you anybody is interested in that derivation, please ask me. Okay, those who are interested only. If you are interested, okay, that will not be coming in the examination. Why? Because it is having an error function. Okay, if you are good at mathematics, very advanced mathematics, then only you can solve this one. Error functions. You might have seen or not, I don't know. Error functions will be there. Depending on that error function, the solution to that equation will be there. Okay. For example, let us say fixed second law of diffusion. Fixed second law. So what is fixed second law? One dimensional. Fixed second law for one dimension is nothing but dou Ca by dou T is equal to dAb dou Ca by dou square Ca by dou Z square. This is one dimensional fixed second law of diffusion. We have derived this formula. Okay, for the three dimensional we have derived, that is dou Ca by dou T is equal to dAb dou square Ca by dou x square plus dou square Ca by dou y square plus dou square Ca by dou z square. So this is three dimensional. We have derived this formula earlier in the earlier classes. Now we are taking only one dimensional. So we have to neglect two dimensions, only one dimension, any x, y, z, anything you can take. Then the solution for this equation is, so since this is an unsteady state, okay, this theory is an unsteady state theory, penetration theory, we have to use the fixed second law of diffusion. Why? Because in fixed second law of diffusion, concentration is a function of time. Dou Ca by dou T is T means time. Ca is a concentration. But whereas why we have used here in the film theory, only fixed first law we have used. Why? Because it is steady state. Okay, there is no role of your time there. That's why we have used steady state fixed first law of diffusion there, and here unsteady state second law, fixed second law here. So the solution for this equation is, so whenever they are asking about the penetration theory, so you have to write this one and you have to explain this phenomena. Okay, the bubble and everything you have to explain, and assumptions you have to write, and the fixed second law of diffusion. Then finally the solution for this equation is Ca naught minus some Ca2 divided by Ca naught minus Cab is equal to error function of some r by root square root 2 dAb into T, where this is T is a time, R is a radius or distance of bubble or distance we can say. Okay, this is, then finally the flux equation Na absorption we can say, that is root of dAb divided by pi t into Ca naught minus Cab. Okay, these three formulas you have to remember. This is fixed second law of diffusion. This is solution for that equation, and finally we have to incorporate into our flux equation. These three formulas you have to remember that one. Whenever they are asking, explain in detail about the film theory or in detail about the penetration theory in particular, you have to write all this one. Explanation, assumptions, draw this figure, fixed second law of diffusion, solution for this equation, and finally the flux equation. If they are asking all the theories, means all the theories you have to write together. But this derivation they will not ask, so it is very difficult. Only in the masters only we will do this one. But I have a solution. Okay, if you want, I can share from my notebook, but it is not required for you. Those who are interested to solve this derivation, a big derivation, 4 to 5 pages derivation will be there. Those who are interested, they can just ask me. I will try to tell you how to derive this one, or otherwise from my notebook I will take photograph and send. Okay, is that clear? Penetration theory.
Yes, sir.
Then next one is a surface renewal theory. Then the last theory is surface renewal theory. Okay, surface renewal theory. So you see here, this is Higby penetration theory. This figure I have shown here, and this absorption operation where the gas is getting from the bottom to top and liquid is from top to bottom. Like this I have shown you. Then assumptions, unsteady state, equilibrium. Then liquid packets will stay in contact with the gas for the same period. Like this I have given, and Fick's second law of diffusion, solution for that one, and flux equation. Finally, what is Kn? So this is flux is directly proportional to the concentration gradient. Apart from this flux and concentration gradient, whatever the variable left is called as a mass transfer coefficient. So Kl, which is function of time, but whereas in the previous theory, it is not function of time, dAB by delta. So this is function of time. Of t means function of time. Root dAB by pi t is the KL, your mass transfer coefficient, KL function of t. So this slide is enough. Okay, you can write in the examination. Then final theory is surface renewal theory. This theory is proposed by Danckwerts. Okay, you have to draw this figure. So how the explanation I will give you. So for example, the this penetration theory, what will happening? So there will be bubble will be there. Onto this bubble, the packets are occupying liquid elements are occupying like this. Okay, 1, 2, 3, 4, 5, 6. Then next stage, what happening? Once again, same bubble will be there. To this bubble, the next packets will be occupying. Then 7, 8, 9, 10, 11, 12. These packets. Then these packets 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, which are there in the initial, they will be dropped to the bottom. And in the next stage, what happens? Furthermore, this bubble will be there, same. The next packets, that is 13, 14, some 15, some 16 will be occupying by dropping your previous packets, that is 6, 7, 8, 9, 10, 11, 12. After dropping these packets, okay, this will be freshly occupied. So this all the packets, whatever 1, 2, 3, 4, 5, 6, all the packets will have a same period of time. For example, this packet is dropping at 1 minute. This element will also be dropping in 1 minute. This is also will be dropping in 1 minute. This is also will dropping in 1 minute. This is also will dropping in 1 minute. Then this sixth element is also dropping in 1 minute. But whereas in the surface renewal theory, all the packets will have an equal probability to be replaced with a fresh element. Okay, for example, this is a bubble. Okay, onto the bubble, there will be some packets, liquid packets or liquid elements. 1, 2, 3, 4, 5 packets. In the next stage, what happens? So, for example, let us say only one is remaining there. 2, 3, 4, 5, 6. Okay. In the first step itself, 3 and 4 packets are dropping. Okay. 3 and 4 packets are dropping. But whereas one will be sliding to the next packet, that is 1, 2, 3, 4, 5, and this will be occupied. Whatever the 3 and 4 has been dropped. Wrongly writing. For example, in the first step, 3 and 4 packets are dropped. Then what happens? They will be sliding like this. That is, this is 1, 2, 3 and 4 already been dropped. That is 5. And this, whatever the 3 and 4 packets dropped, no, that packet places will be occupied by a fresh packet 6 and 5. So this 3 and 4 will drop at 1 minute. And this 1 and 2 will be dropped at some 2 minutes. Okay, after this dropping, the further fresh packet will be occupying. So the packet, whatever this element are dropping, no, that period need not to be same for every period, every packet, every element. Okay, one packet will be dropping at 1 minute, other packet will be dropping. For example, first element is dropping at 1 minute. It need not to be same. That second packet needs to be dropped in 1 minute. It need not to be same. It can drop in 5 minutes, or it can drop in 6 minutes or 7 minutes, or it may take in for 1 hour also. No problem. But what this surface renewal theory, what they want to say is every packet will have their individual period of time. Not all the elements will have a same period of time. But whereas in the penetration theory, all the elements will have a same period of time. If this all the elements are dropping at 1 minute, so all 6 elements will be dropping at 1 minute, and a fresh packet of 7, 8, 9, 10, 11, 12 will be coming at that 1 minute. And for next 1 minute, if these elements are dropping, a fresh packets of elements will be next 6 packets of element will be once again replacing it. But here it need not to be same. First packet will be dropping at 1 minute, second packet will be dropping at 3 minutes or 5 minutes, 6 minutes, like this. Every packet will have their individual time. Okay, not equal time. So whatever the portion are there, that will be replaced. Every packet will have a probability, equal probability to be replaced by the fresh packet. So assumptions are there for this surface renewal theory also. That assumptions are, so first assumption is the liquid elements at the interface are being randomly swapped, very randomly swapped by fresh elements from bulk. Okay, bulk of your liquid phase. Then second is at any moment if you verify that one, each of the liquid elements at the surface has the same probability to being substituted by fresh element. Okay, every element will have a same probability, fresh element. And third is unsteady state mass transfer will take place. So this theory is also unsteady state mass transfer theory. Mass transfer will takes place. Okay, the penetration theory and surface renewal theory, both theories are the unsteady state theory, whereas film theory is a steady state theory. Okay, so first assumption is every liquid element will be randomly swapped. Okay, the liquid elements will be replaced with a fresh liquid element, but at the same time every liquid element will have a same probability of replacement of this element by the fresh elements from the bulk of the liquid phase. That's what the second assumption. And third assumption is steady state mass transfer will occur. So then this finally one correlation or one expression has been given by this surface renewal theory, that is Na absorption is equal to root of S DAB Ca0 minus Ca1 or something, a bulk phase, whatever it may be. Then we can say flux is directly proportional to the concentration gradient or driving force. So this is a driving force. So this is a flux. So apart from the driving force and flux, whatever left is called as a mass transfer coefficient, that is Kn, which is also a unsteady state function. Then this is Na absorption is equal to KL Ca0 minus Ca1, where KL is a mass transfer coefficient which is given as S root of S DAB. So what is this S? So where S is the fraction of surface renewed in unit time. Okay, at particular moment of time, what is the fraction that is renewed? For example, in the penetration theory, if you see at 1 minute, if you check, all these elements 1, 2, 3, 4 will be dropped. Okay, fraction of the surface which is replaced with the fresh element means here 6. Okay, Here what happens in the surface renewal theory, only 2 packets has been dropped, but 2 freshly occupied packets will come. But here all the 6 packets will be dropped at the same period of time. And it's the same period of time, all remaining packets will be occupying the droplet. But here every packet will have a different period of time. That's why we have to check at each moment. For example, time we will fix at 1 minute, how many packets of the previous case has been dropped. 3 and 4 has been dropped at 1 minute. So fraction of surface which is replaced means 6 packets are there initially, 5 packets are there initially. So that is 2 packets has been dropped and remaining 5 packets, okay, 2 by 5 has been replaced. Like this we have to define this fraction of elements that has been replaced by the fresh elements. That is surface renewal theory. Is that clear? Surface renewal theory.
Yes, sir.
Yes, sir.
Yeah. If you read the notebook once again, it will be very clear. Okay, these are very small theories only. Not a big derivations are also not there. This film theory, you already know this derivation. Yeah, this equimolar counter diffusion derivation only. But only in place of Z, we are writing film thickness delta. That's the only difference there. Nothing more than that one. And here penetration theory, you have to remember this fixed second law of diffusion. We already derived this 3-dimensional. Out of this only 1 dimension, anything x, y or z, anything you take it, and solution you have to write this one. Then the flux equation. Okay, that is enough for your syllabus. Okay, not the big derivation is also not there here. And the surface renewal theory, it has directly given the formula. Okay, they have given NAAB is equal to root of STAB into CA0 minus CA1. That they have given. You have to remember that equation. That's it. And apart from that one, this diagrams and assumptions you have to state who proposed that theory and everything. Okay, here see the surface renewal theory is proposed by Danckwerts and assumptions are this one, and they have given this equation. S is the fraction of surface that is renewed for unit time in second inverse. Then KL average is nothing but your mass transfer coefficient, which is root of SDAB. This slide, in this slides entirely whatever is required that has been given. Many times they are asking explain in detail about the theories of mass transfer coefficient, theories of mass transfer. Okay, then you have to write all the 3 theories. Okay, in some cases they are asking explain in detail about the 2 film theory or 2 resistance theory, or derive the derivation for 2 film theory or 2 resistance theory. So this is somewhat a bigger derivation, somewhat conceptual derivation here. So that we will see in the next class, but concept I will explain you now itself. So just try to observe this concept. What is there? 2 film theory or 2 resistance theory we can call. Okay, for your study it will be easy if you study and come for the next class. 2 film or 2 resistance theory. Okay, sometimes in the examination they are asking us to derive the mass transfer coefficient for 2 resistance or 2 film theory. Okay, 2 resistance or 2 film theory, or otherwise once one again form of this question is also possible. That form of question is explain, derive the relationship between, derive the relationship between individual mass transfer coefficient and overall mass transfer coefficient. Okay, 3 possibilities are there. Questions in this particular for this answer. What is that one? One is explain or derive the mass transfer coefficient for the 2 resistance theory, or derive the mass transfer coefficient for the 2 film theory. Then also same answer. The next possibility is derive the relationship between individual mass transfer coefficient and overall mass transfer coefficient. Then also the problem is same thing. Okay, the solution is same thing. So how to derive this one? For example, the same tower I am taking once again. That is, gas is flowing from bottom to top. This is gas inlet. This is liquid outlet. Sorry, inlet. Liquid inlet. And liquid will be flowing from the top to bottom, and gas will be flowing from the bottom to top like this bubbles. Okay, they will be intersecting at each other. according to film theory, what they are saying, if there is some surface, this column is some surface, what it is saying, some thin film will be formed like this. That thin film will have a thickness of delta, and throughout this film only mass transfer will take place from Ca0 to Cab, and after this film the concentration will be same. So this film theory is saying here there are two film. Why? Because there are two phases. One is liquid, one is gas is there. This is liquid phase, this is gas phase. But according to film theory, so every mass transfer will take place inside the film only. But here liquid is also there, gas is also there. For that one, how to define that one? For example, let us say, this is gas and liquid interface. Okay, gas and liquid interface. And here at one side of this one, maybe some liquid film. Okay, this is liquid film. And another side will be some gas film. This is gas film of some thickness. Then here bulk phase of gas, bulk gas, or here this is liquid in bulk or bulk liquid. Bulk liquid means nothing but the streams, gas stream. This is gas stream inlet stream, and this is liquid stream inlet. That is bulk we will call. Why? Because large amount of solute will be present in the bulk phase only. So mass transfer is taking place from gas phase to the liquid phase. We know that one. So in the bulk of the gas phase, the component A will be, so this is gas phase. For the gas phase, the expression of concentration in terms of pressure is very easy. So throughout this bulk phase, the pressure of this gas component A will be same. So this is uniform line like this. Okay, until here it is PA only. So after film, after this liquid film, okay, this film thickness will be, for example, this is a mass transfer zone at initial condition at 0. So this is interface of the gas film, that is Zg. Okay, this is thickness of the gas film throughout this one. And this is once again in next film will be started, that is 0. Once again this is new mass transfer zone. So this thickness will be, this is Zg, and this thickness will be Zl. So 0 to thickness of the liquid film. So this is thickness of the gas film, this is thickness of the liquid film. So together we can say that, so this is initial mass transfer at the start of the mass transfer, and this is final, that is Z. So overall thickness of the film is nothing but Z is equal to, so this Z is equal to thickness of the gas film plus thickness of the liquid film. So the partial pressure of component A is PA, and once it just touches the gas film, the concentration of this gas component A in the gas will be dropped like this. Okay, it will attain an interfacial pressure, that is PAI, interfacial pressure, partial pressure of component A. Then from here the liquid region will start. This is liquid film, this is gas film. So from here liquid region will start. So that is the concentration will comes as a concentration of interface, concentration of component A at interface. Why? Because this is liquid phase. For the liquid phase, expression of concentration is very easy, but for the gas phase the concentrations will be expressed usually in pressures. So from CAI to, once again it will be dropped to the bulk of the gas phase concentration, that is some, from here the concentration will be say bulk of the gas liquid phase concentration, that is concentration of component A, Ca. Then equally, whenever the liquid is coming from the top to bottom and gas is going from the bottom to top, this is happening, some solubility will be there here. This is for gas phase. Equally, the liquid phase concentration will also be there. The equilibrium liquid phase concentration is called as Ca star. In the gas bulk phase, the equilibrium concentration in the liquid phase is Ca star. And similarly here also, In the bulk of the liquid phase, equilibrium concentration in the gas phase is also expressed as Pa star. Okay, this is overall picture. Okay, if you know this, if you understand this picture, the derivation is very easy. If you don't understand this picture, the derivation is very hard. You cannot understand the terminology. If why we are why at the higher pressure is there, why here also the constant is there pressure, and why here it is dropping, okay, why here it is further dropping, and this Pa star will be lower than Pa, and this Ca star will be higher than Ca. You can understand throughout this graph. If you understand this graph, it is very easy to calculate. Otherwise it's very problematic. Okay, before coming to the next class, you just try to read the notes once again, and this graph will be there. Just try to understand this graph. Many times they are asking this one. Is that clear?
Yes, sir.
Yeah. Okay, then thank you for listening.
Thank you, sir.
Thank you.